Okay, so thank you for coming. I'm going to talk about coupling selection rules and heterotic Orbifold compactifications. This is work done in collaboration with Tatsuo Kobayashi, Saul Ramos Sanchez, and Yvonne Zavala. And if you're interested in the topic, please also look out for this paper here. Heterotic Orbifolds continue to be a promising framework for string phenomenology, representing simple, globally consistent constructions with a clear geometrical interpretation. By now, we have hundreds of models whose spectrum corresponds to that of the MSSM with no chiral exotics. And in order to understand the dynamics of these constructions, issues like decoupling of vector-like exotics, moduli stabilization, and SUSY breaking, quark and lepton masses, we require the couplings in the low-energy effective field theory. So as we've heard, one of the most attractive features of heterotic orbifolds is that they correspond to free conformal field theories, and therefore we can compute directly, explicitly the string couplings, and from that infer the low-energy effective field theory. The first question to ask will be which couplings are vanishing, and this is determined by string selection rules. So I will first review some Orbifold CFT basics, then I'll outline how to derive coupling selection rules from the general structure of the L-point correlation functions in the CFT, and I'll conclude. Let me first fix my notation. So we construct the heterotic string by combining a right-moving superstring with 10-dimensional bosonic coordinates x and their superpartners, with a left-moving bosonic string where the 16 extra bosonic coordinates parameterize our gauge degrees of freedom. We'll compactify on a toroidal orbifold where the underlying lattice of the torus is factorizable, so a product of 3 two-dimensional tori, and we'll choose our orbifold twist to be a Zn symmetry of our torus lattice lambda. The orbifold boundary conditions alter the spectrum of string states compared to flat 10D. In particular, a number of new sectors emerge, which we call kth twisted sectors. These are sectors that contain strings that are closed thanks to the orbifold twist and the lattice shifts. Here and throughout J, we'll label the complex planes of our orbifold, 3 complex planes of the orbifold, and K labels the number of times that we apply the orbifold twist in order to close the string, leading to a kth twisted sector. The twisted sectors are, of course, localized at the fixed points of the orbifold geometry. The states in the string Hilbert space correspond to fields in the CFT, and we will require the vertex operators in the CFT, which describe the emission of twisted fields. Here I give you an example, a vertex operator describing the emission of a twisted bosonic field, and it's composed of a number of different parts. We have 5 free bosonic fields which correspond to the fermions, the right-moving fermions after bosonization, and these carry a momentum which we call H momentum. The gauge degrees of freedom carry, of course, the gauge quantum numbers, which we will call gauge momentum. We have the twist fields, which incorporate the non-trivial boundary conditions of the twisted sectors. These are labeled by K, labeling the kth twisted sector, and the fixed point on which the twisted field is, the twisted string is localized in the orbifold geometry. And importantly for what comes, we have a number of bosonic, holomorphic, and anti-holomorphic oscillators, which are involved in producing excited massless states, and they are counted by holomorphic and anti-holomorphic oscillator numbers. So we want to derive L-point couplings in holomorphic superpotential, and when you look at the general structure of n equals 1 4D supergravity, it turns out that the easiest way to identify these terms is by considering couplings of the type fermion-fermion and L-2 bosons. So we want to compute string tree-level correlation functions between 2 fermion vertex operators and L-2 bosonic vertex operators. So just as the vertex operators split up into different parts, because we have a free theory, the correlation function also factors into several parts. So here I've written down the general form for the 3-point correlation function. the general higher order correlation functions can also be treated. It's just slightly more complicated. So for the talk, I will focus on 3-point functions. So each part has its own selection rule. The easiest part to deal with is, of course, the bosonized fermions and the gauge bosons. And this can be computed trivially analogously to the Veziano amplitude, for example. And as a consequence, one finds that the correlation functions have to be vanishing unless the gauge momentum is conserved. This corresponds to gauge invariance, and unless the H momentum is conserved. The twist fields lead to a selection rule that is known as the space group selection rule. It is associated with the boundary conditions of the twistor strings, and it includes what is known as the point group selection rule, which is that a coupling between sectors K1, K2 and K3 twisted sectors is only allowed if K1 plus K2 plus K3 is equal to 0 mod n for a Zn orbifold. So the non-trivial part of the correlation function is the one that involves the twist fields and the bosonic oscillators. From now on, NL and NL bar will count the total number of oscillators that appear in the correlation function with contributions from all the different vertex operators. So we can make progress with this expression by splitting up the fields into classical solutions to the equations of motion and the quantum fluctuations about them. Physically, these classical solutions correspond to worldsheet instanton solutions, which describe worldsheets stretching, wrapping the orbifold, and attached to the fixed points F1, F2, and F3 involved in the coupling. So the explicit form of the classical solutions is known, it can be computed, and it's determined completely by the local and global monogamy conditions. And what will be important for us is that it turns out that they are proportional to particular torus coset lattice vectors, so shifted vectors on the torus lattice. And moreover, that it can happen that depending on the twisted sectors involved in the coupling, it can happen that the only way to satisfy the local and global monogamy conditions in such a way that the classical action converges is with vanishing solutions. Okay? So having split the bosonic coordinate fields into the classical and quantum parts, we can plug that into the correlation function, and the correlation function will also split into a number of different terms. We can just expand these powers using the binomial expansion, and now we'll be ready to derive a new string coupling selection rule. So we need two results. One follows from the basic OPEs of the CFT, and that is that for the quantum part of the correlation function with R holomorphic oscillators and S anti-holomorphic oscillators, this correlation function is 0 unless the number of holomorphic oscillators and the number of anti-holomorphic indices oscillators is equal. Moreover, as I alluded to, the local and global constraints on the classical solutions imply that depending on the twisted sectors involved, it happens that for the 3-point couplings, either anti-holomorphic instantons vanish, so we have this condition, or holomorphic instantons vanish, or both vanish. Now you can plug all this in to the correlation function, do some simple algebra, and we arrive at what we have called Rule 5 for historical reasons, and this can be summarized as follows. So if the twisted sectors involved in a coupling are such that only holomorphic instantons are allowed, then the number of holomorphic oscillators in a correlation function has to be greater than or equal to the number of anti-holomorphic oscillators. Similarly, if the twisted sectors are such that only anti-holomorphic instantons are allowed, holomorphic oscillators, the number of holomorphic oscillators should be less than or equal to anti-holomorphic oscillators, or if the twisted sectors are such that no instantons are allowed, the number of bosonic or holomorphic oscillators has to be equal to the number of anti-holomorphic oscillators. So now we are ready to derive a further rule, which was actually discussed in detail back in '88 by Font, Ibanez, Niles, and Cavero, but for some reason has not been applied in the current literature. So let me, for illustration, show you the case where only holomorphic instantons are allowed. So the twistor sectors are such that only holomorphic instantons are allowed. And having applied rule 5, the 3-point function reduces to this simple form where I've suppressed the quantum part. And what will be important for us is that we have a sum over the classical solutions. So this corresponds to the different classical solutions correspond to the worldsheet instantons wrapping the orbifold multiple times. So as I alluded to before, the classical solutions turn out to be proportional to shifted lattice vectors. So F2 and F1 are two of the fixed points involved in the coupling. Lambda J are the lattice vectors. And the set of classical solutions turns out to enjoy a Z Pj symmetry where Pj is the order of the twist in the jth plane. And using that symmetry, one can show that then this combination of the number of holomorphic oscillators minus the number of anti-holomorphic oscillators must be equal to 0 mod Pj, where Pj is the order of the orbifold twist in the jth plane. Again, this is called twist invariance. And together with the H momentum conservation that I discussed earlier at the beginning, this can be combined to derive an R-charge conservation condition, which is what is being applied in the literature today. But that's not the full story. So one notices that when all the fixed points in a coupling, when all the fields in a coupling are localized at the same fixed point, the classical solutions turn out to be proportional to actually the torus lattice vectors. And this means that the sets of classical solutions can enjoy a larger symmetry. So they enjoy the full lattice symmetry, which can be, of course, larger than the twist symmetry. For example, we might take a Z3 twist on a lattice which enjoys a Z6 symmetry. And the upshot is that the correlation functions will be vanishing unless the number of holomorphic oscillators minus the number of anti-holomorphic oscillators is equal to 0 mod Kj, where Kj is the order of the lattice symmetry. So let me conclude. So to build realistic models, we have to understand the couplings in the low energy effective field theory. The selection rules for superpotential couplings can be identified by looking at the general structure of L-point string tree-level correlation functions. The space group selection rule, gauge invariance, and R-charge invariance, which is what is being applied in the current literature, is sufficient for non-oscillator couplings. But couplings between excited massless states and higher order couplings involve oscillators. Then the structure of the worldsheet instanton solutions leads to additional stringy selection rules. So we have rule 4, which occurs when the torus lattice has extra symmetries beyond the orbifold twist, and rule 5 when local and global constraints imply that the instanton solutions mediating the couplings are vanishing. So these rules have to be implied, all of them have to be implied when computing allowed superpotential couplings. Let me just end by noting that the ultimate objective is, of course, the full low energy effective field theory. So we would like to be able to derive not only the terms in the holomorphic superpotential, but the Kähler potential, the gauge kinetic terms, and the Fourier-Iliopoulos terms. What has been least studied is the Kähler potential, and it would be interesting it would be important to know what the allowed terms are there. Thank you.
Questions? Maybe I didn't get this. Rule 4 and 5, do they only apply to twisted sector couplings?
No, that's not true. So one can play the same game, of course, with the untwisted sectors. So with the untwisted sectors, the rules are actually particularly strong, because then, if I remember right, the worldsheet instanton solutions are simply not there. So that imposes stronger conditions on the oscillator numbers, of course, by rule 5.
So you present here selection rules. It's also really possible to just calculate it properly. And to what order could you really go, really explicitly, that you really just get numbers out?
So explicit computations have been done, of course, for order 3 ground state fields. And there have been some explicit computations also for order 3 excited massless fields, but not so many, I should say, by Balin and Love and someone else, I forgot, sorry. There are some people have begun to study higher order couplings explicitly. There's a paper by Choi and Kobayashi and Kim, I'm sorry, I forget right now. But I would say that one has to do more work to understand fully, especially the higher order.
Yeah, because the paper by Kobayashi and so on in the end parameterize things as a certain integral, and I've been looking at it and I don't know what to do.
Yeah, I agree. It would be interesting, important.
Questions? Question myself. You have the rules. Have you used those rules to the models that people have been building recently and see there some couplings that have been assumed to be there and not actually not there? Or?
Yeah. So I promised that question was not planted.
Always very original.
So just to show you that indeed the rules are non-trivial. So we looked at just a couple of explicit models and counted the number of allowed couplings, just applying the standard rules of space group selection, arbitrary conservation, gauge invariance, and that's the first column, and the second column is without. It was with the rules 4 and 5, and both of them have kill couplings.
So do they kill important couplings?
Yes.
So like in the standard model sec part of your theory?
So far we have looked we've only begun to look at this, and we've seen that, for example, the rank of the mass matrices for decoupling vector-like exotics is still full, so that's good news. There are still photon decay 5 operators present, some, so that's also good news, and and that's as far as we've gone so far.
Okay, well, thank you very much.
Thank you.